Hi guys, welcome back to my channel. Today we're going to be looking at forces that depend on time. At this point we're kind of familiar with Newton's second law, which is that force is equal to mass times acceleration. This formula we can only use when acceleration is constant, but in the real world this often isn't true. So instead what we can do is we can represent acceleration as a function of time, and we can do that using differential equations. So acceleration is equal to the second derivative of x, which in this case represents displacement, or we could write this as the change in velocity over the change in time, or we could represent this as our force as a function divided by our mass. So this is called the equation of motion. And what we can effectively do, rather than writing that force is equal to mass times acceleration, when acceleration is constant, we can write force as a function of time is equal to the mass times the acceleration, which is also a function. So really that's the key difference. Rather than force and acceleration being constant, they are now functions. So let's have a look at this example here. A particle of mass 5 kilograms moves in a straight line and is acted upon by a force of 60 T takes 60 newtons. So we can see here how force is a function now, where T is the time in seconds. Initially, the particle is at the origin, and after 1 second, the particle is 52 meters to the left of the origin. Calculate when the particle first comes to rest. So I've written down my key information here, and I'm going to substitute this into my formula. So we know that force as a function of time is going to be equal to the mass times by the acceleration. So our force as a function of time is going to be 60 T take 60, and that will be equal to 5 kilograms times by our acceleration. So going ahead now, what I can do is I can simplify by dividing through both sides by 5, and that's going to be equivalent to my acceleration. So what we're looking for now, we've got acceleration, and acceleration is the same as the derivative of velocity over time. So let's replace this. So we have 12t take 12 is equal to dv dt. So now we have a differential equation that we can solve using integration. And I can integrate both sides with respect to t, and I can solve for velocity as a function of time here. Now we can't go ahead and just substitute in the values that we have in the expression in our question here, because initially, even though the particle is at the origin and after 1 second the particle is 52 meters to the left of the origin, this isn't the velocity, this is the displacement. So we're going to have to integrate again to find our displacement. So now that we have our function for displacement, we can go ahead and substitute in the values that we have. So after 1 second, the particle is 52 meters to the left of the origin, and initially they are at the origin. Okay, so now that we've substituted each of those values in, we've determined that C2 was equal to 0 and C1 was equal to negative 48. So I've substituted that back into my original equation for velocity so that I can determine when the particle first comes to rest. So in other words, when the velocity is equal to 0. Just realized I've done something a little silly here, so that's going to change my answer. That should actually be a negative value there, so this is going to be different. So this should actually be t minus 4t plus 2. So that means t is going to be equal to positive 4, or t is going to be equal to negative 2. Now in this particular context, it doesn't really make sense to have negative time, so we're not going to include that value. So therefore, after 4 seconds, the particle comes to rest. So that's how we use forces that depend on time, and really the important takeaway from this is that we need to make sure that we are using this slightly different formula in order to calculate our functions of forces as a function of time and of acceleration as a function of time. Once we've determined that, then we can go ahead and we can use differential equations to solve for functions for velocity, or if we need to, for displacement. Alright guys, that's all for today. I will see you in the next one.